Saxon Advanced Mathematics, Lesson 73. Welcome to New Notebook Day. I'm always excited when it's a new notebook. We're just tearing through them this year, filling them up. We're on Lesson 73. We are at the beginning of week 20. 20 weeks of study. You guys, that's a lot. I am cheering you on. That is so much homework. That is hundreds of homework problems. So I applaud your efforts. I congratulate you on making it as far as you have. And I've got a very straightforward lesson for you today. It's geometry, but it's got a lot of algebra in it. And it's kind of fun, I think, once you get the hang of it. There are only 2 examples, P.S., which is always nice. All right, regular polygons can be inscribed in a circle, written within a circle. So let me draw a circle and show you what I mean. Here's a circle, and here's a regular polygon. Pretend it's perfect. That's a triangle within a circle, right? They have the same center. And look what I can do. I can divide this triangle. Let me use a different color. I can divide this triangle up into little triangles where the one side of the triangle is equal to the radius of the circle, isn't it? Interesting. We can do it with other shapes as well. Here's another circle. Again, pretend it's perfect. And here's another regular. By regular, remember, we mean same side, same angles. A regular polygon inside of it. And we can do the same thing. We can divide this into 4 triangles. Each triangle has one side, 2 sides that are equal to the radius of the circle. And here's a 5-sided. Oh, I cannot draw these accurately. Oh, this one's not bad. There's 5-sided, right? A pentagon inside. And again, we can divide this into triangles. And now I want to talk about these triangles. Within each triangle, we could draw 2 isosceles right triangles, couldn't we? And we could use trig functions on these little triangles if we so desired, couldn't we? Interesting. And it goes on up. We can go, this is 3-sided, 4-sided, 5-sided, 6, 7, 8, 9, 10. We can go all the way up and continue to draw regular polygons inside of them. What we're going to practice doing is finding the area and the perimeter of these inscribed rectangular polygons. And we have the tools to do it. It's kind of fun. The last thing I want to tell you is kind of obscure, but it comes up every once in a while and I want you to see it. Let's do it with a pentagon. Okay, so I'm going to do this one again. I'm going to try my best to draw a decent one. Okay, there it is. We draw the 5 triangles inside, right? And we notice that this pentagon is written within the circle, right? The outer green circle. The green pentagon fits within the green circle. This blue line goes to the vertices in each corner of the pentagon, the corners, and they're equal to the radius, right? But look what happens if we draw another set of lines, like I did here, to divide each triangle in half. This orange line is the altitude or height of the triangles. And you ready to see something crazy? If we draw a circle inside of the polygon, so in this case, now this is hard to draw perfectly, but let me try. I'm drawing another circle inside of the green pentagon. It represents the radius of the inscribed, uh-oh, I'm running out of orange juice here. Circle. What in the world am I talking about? Look how it goes. Circle, pentagon, green pentagon. The radius of the outer circle equals the length to the vertex, right? These blue lines go from the center to the corners of the pentagon. That's the radius of the big circle. But now I draw a little circle inside of the polygon, and I add these orange lines that are what's going right down the middle of each of the first triangles, and that gives me the radius of another circle. So we can go from outer circle to pentagon to triangles to a new circle. And if we really wanted to blow our minds, we could continue that process, right? They fit inside of each other. Circle, pentagon, triangle, circle. It's crazy how it is like looking, you know how if you line two mirrors up and you just keep looking further and further down? And I think the last Star Wars movie had a scene like that. Didn't they? Rey's in the cave. And she sees like all the rays going in either direction. Yeah, that's kind of what this makes me think of. So we're not going to do a lot of calculation with this, but I just wanted you to be aware of that. What we're going to do is we're going to go back to pictures like this. Our first one is a pentagon, and we're going to practice finding the area and the perimeter of these. Now I'm just tripped out. My grandparents had a bathroom fairly small, but they had two medicine cabinets directly opposite each other, so I could open the doors and make that mirror thing work. I spent a lot of time getting my mind blown by looking at that. And you know, I could adjust, because the mirrors were on hinges, so I could adjust ever so slightly and make the tunnels change direction. I love that. Okay. Example 73.1. Are you ready? Find the area and the perimeter of a regular pentagon, 5 sides, John said that is inscribed in a circle whose radius is 6 units. Okay, so we start with the circle. We draw a pentagon. Oh, I'm getting my practice at drawing pentagons tested, aren't I? Okay, not terrible. The circle's radius is 6 units. Okay, so the center of the pentagon is the center of the circle. The radius goes out to the vertex, which makes sense because the vertex touches the edge. This is 6 units. Okay, now I'm going to draw one of these triangles. This is also 6 units. And I can put a line here. I'm going to dot it. And I'm going to turn this into 2 isosceles triangles. I know that if I wanted to, I could draw a circle inside of this pentagon. And this line would become the radius of the inside circle. But I'm not going to do that. That's just to mess with you. What I want to do is I want to find the length of this side, because then I can find the perimeter. And then I want to find the area of at least one of these triangles, because then I could go for broke, couldn't I? I could figure it all out. All right. How am I going to find the height of this triangle? How in the actual heck? Well, what I want to do is I want to draw a bigger version of these triangles so we can write on them a little bit more. All right, so pretend it's exactly the same. It's not exactly the same. There's my dotted line. There's this. This is 6. Here, I'll circle both of them. This is 6, right? I know that if I can find out that length, then this whole length will be 2 times that. Because even though my picture doesn't look like it, these are identical. I need an angle. I don't have any angles. How could I find an angle? Well, I'd like to have this angle, but I think I can figure out the whole angle going across both of them because there are 5. So if I take the full circle, 360 degrees, and I divide it by 5, because there are 5 of these triangles, that will give me, what, 72 degrees. for this whole bit, but then this much, 72 degrees is that. But if I take 72 and divide it by 2, this much alone will be 36 degrees. Oh. Now, it's getting interesting because now I have an angle and a side. And that is enough to give me another side. This, if this is my angle, this is my perspective, this is the opposite, and this is the hypotenuse. So that tells me that the sine of 36 degrees equals opposite x over hypotenuse 6. And then I can switch that up and get 6 times the sine of 36 degrees equals x, this side, and I run that through my calculator, and I get x equals 3.53. That's this much. Okay? Okay, I feel good about that. Now, I have to multiply it by 2 to get the amount for this triangle. But then I have to get all the other triangles all the way around. Well, I know I have 5 triangles that go all the way around. I could draw them in easily, right? Right? 1, 2, 3, 4, 5. But I also know that I'm splitting each one in half, right? This 3.53 represents half of one of the 5 triangles. So if I multiply 3.53 times 10 for 5 triangles, each divided in half, then that will give me the perimeter of the whole monstrous thing. So the perimeter equals 35.3. I just bumped this. No, I did it. I didn't. No, that's right. I'm multiplying by 10. I was trying to move the decimal more places than that. 35.3, what are my units? They don't say, so it's just called units. I mean, they call them units. That's the perimeter. All right? I used my information about the existing side, which is the hypotenuse. I figured out how big that angle is for half of it. I can't do the whole thing because I can't use sine that way, right? I want to just make a right triangle here so I can use my trig functions the normal way. I don't have enough information to use law of sines on the big thing. So, maybe I do, but trig functions the normal way work better here. I figured out this angle, they gave me this. I wanted this because I want to find the perimeter. And here's my calculation. Now I need to find the area of this triangle, either the partial one or the whole one, it doesn't matter. So, let's remember to find the area. Okay, so first I was working on perimeter. Let me write that. Now we're working on the area. The area of a triangle is the base times the height divided by 2. The base, I'm just going to do the whole triangle. The base equals this doubled, right? Because x was only half of it. To get the base of the whole triangle, I need to double that. So that would be what? 7.06. Now, how about the height? How are we going to find the height of this? Well, I can go back to my trig functions, and this time I can use 6 times the cosine of 36 degrees. That would be the adjacent, right? Cosine will give me the adjacent over the hypotenuse, and I just bumped the hypotenuse up there, right? Okay, so to the calculators we go, and we get h equals 4.85. So to find the area of one full triangle, right? not a half triangle. I'm using the base of the whole thing, right? 7.06. So this, I'll need to multiply whatever I get times 5, not times 10. I could have done it the other way. I could have left the base as just half and then multiplied it by 10. Doesn't matter how you do it, whichever seems better for you. So the area of one full triangle equals the base, 7.06, times the height, 4.85, divided by los dos, and that equals, oh, and let's just do this. Flip my page. So the area of all 5 triangles will be the area of one triangle, 7.06 times 4.85 divided by 2 times 5 over 1. That's all the triangles. And the answer we get is 85.6 units squared, and that's the area of the whole pentagon. All right, so the moral of the story is we take the information that we have, which is an angle and a hypotenuse. We use sine to solve for this part of the perimeter, and then we multiply it up to get the whole perimeter. Then we use cosine to get this side, which is the height we need for our triangle calculation. Okay? So the perimeter, we use the sine. The area, we use the cosine to get the height. All right? I mean, it was involved, but that was kind of fun, wasn't it? We know so much more than we think we know. Example 73.2. This is our last example. I'm sorry. You're gonna have to find something better than this to do after you're done. I don't know how. Well, I guess your homework. Okay, the perimeter of a regular polygon of 8 sides is 48. So we have an 8-sided object, an octagon, like a stop sign, and the perimeter equals 48. Find the area of the polygon. All right, John's just making it a little bit tricky for us, but we can manage. That's fine. So what I'm gonna do is I'm gonna draw not the whole 8-sided thing, but I'm going to just tuck what I'm gonna pretend is one of those 8 triangles in here, okay? And I know I'm probably gonna wanna do that so that I can use trig functions on there, but I need to find the size of this angle. So I'm gonna take 360 and I'm gonna divide it by, let's do it in 8. We'll do it in 2 steps. That will be 45 degrees per triangle. But I want to split my triangle in half, so that means this angle will be 22.5 degrees for just the half the triangle. I cut that number in half. Okay, now this time we don't know the hypotenuse. This time the number we know has to do with the perimeter. 8 sides, the perimeter is 48. That means the total of this is 6. And that means this side is 3. Last time we were given the lengths of the radius of the circle, and we knew that was the outside edge of our triangle. This time we're given the base. Oh, that means we're gonna have to use our information a little bit better, aren't we? Let me redraw just the part of the triangle we want to use the trig functions on. The base is 3. Okay, there's the right angle. This is 22.5 degrees. And we're trying to find the area of the triangle, so that means we need to know this height, right? So I'm gonna call that, oh, I'll just call that A, right? That's the length of this side. Okay, we've got the opposite, and we want the adjacent, we have the angle. So that sounds like a case for tangent. The tangent of 22.5, not 225. 22.5 degrees equals the opposite over the adjacent, right? Over Arthur. So it's 3 over A. Do some cross multiplying, algebra, slide it around in order to get this ready for the calculator, and we get A equals 3 over the tangent of 22.5 degrees. And when we push that through, we find that that is equal to 7.24. Remember, for this calculation, you'll do 3 divided by parentheses, 22.5 tangent, end parentheses equals. All right, so now we're ready to do our calculation here. The area of a triangle equals base times height divided by 2. So in our case, our bases, now we can do it one of 2 ways. We can consider this one of 16 triangles, right? If we look at just the half, then we can multiply it by 16. I prefer to do this. This is the base of half of our triangle. If we want the base of our whole triangle, we'll use 6 times the height. The height we don't have to adjust, 7.24. We divide it by 2 because that's the formula, and then we'll multiply it by 8. We're using the base of the full triangle, so we don't have to double count for each triangle. There are 8 sides, so that means 8 triangles. So we'll just multiply this times 8 over 1, right? Because this is for 1 triangle and we want it for 8. And our final answer then should be that the area of the polygon equals 173.76 units squared. You may use a calculator to simplify that. And here's what I'm doing. That reduces to 3. This is 24. 24 times 7 is a lot like 7 quarters, right? Because quarters are worth 25 cents each. I don't know why. Thinking of multiplying in 25s is quarters to me. So 7 quarters is $1.75. So this looks pretty reasonable, doesn't it? This needs a square on it. John tells me this is the right answer. Yay. The hardest part of these problems is keeping straight. Am I looking at a full triangle or am I looking at a partial triangle? When we use the trig functions, we have to look at the partial triangle in order to get that right angle that we need for the trig functions to work. And that's fine, but if we're working in half triangles, then we have to multiply that. We have to remember that we don't have 8 of them, we have 16 of them. But we also can say, never mind, I've thought about half triangles for a while, but now when I do the area, I want to think about the whole triangle. So I'm going to use the base for the big triangle, which in this case is 6 rather than 3. And if I do that, then I'm only thinking about 8 triangles, not 16. That is kind of weird. So you just have to get your head wrapped around whether you're talking about the whole triangle or the partial triangle, and just make sure you don't lose your mind. I mean, that's always a good rule of thumb, right? But just keep track of which size of triangle you're looking at. Lesson 74 is complete. I hope you enjoyed it. I think that is a solid lesson for this class. Next lesson is going to be really fun because we're going to learn our 5th strategy for solving systems of equations. 5. Can you imagine? It's so exciting. Okay, that's all for lesson 73. Thank you. Goodbye.